So hello everyone, we'll be starting fluid mechanics. So this course will be break down into three parts. First will be introduction. Second being fluid statics, and third fluid kinetics. Okay, so introduction part will be understanding all the definitions and the basic concepts of fluid statics and fluid kinetics. But just the introduction part, what are they? And then we'll be hopping into fluid statics and fluid statics. So just giving a brief introduction. Fluid statics is the mechanics or the physics of fluids which are not in motion. The stable fluids like like water in your cup, water in a dam, etc. Fluid kinetics refers to the motion of a fluid like water flowing through your pipe, like rivers flowing, etc. So let's, without wasting any time, we'll just start. So first of all, we'll be understanding what is a fluid. Basic question: what is a fluid? So yeah, most of us will be telling anything which flows is fluid, but we'll be going in a bit mathematical way, which is more related to physics and involving physics in it. So by method of physics, we can tell any solid which, on application of shear stress, changes its form and is not returned to its original form, or not even partially, when the shear stress is removed. Okay, so I'll be explaining by drawing diagram. So let us assume a solid block. When it is applied to a shear stress, it gets deformed by an angle gamma. So a solid, when a shear stress is applied on a solid attains an equilibrium after a certain time, or in certain deflection of an angle, as you can see, gamma. But a fluid are those materials which, on application of shear stress, does not attain equilibrium and continue with its deformation. Shear stress is applied, the fluid will continue to deform. You can see from here to here to here, the angle is being increased. So this behavior of a fluid of not returning to its original form, not even partially, is known as zero memory property of a fluid. So writing the definition, we can write in case of shear stress, it keeps on deforming continuously. Like so, in case of shear stress, it keeps on deforming continuously, unlike solids which attain an equilibrium after a certain deflection or time. Okay, so this is the basic definition of what are fluids. In more general way, we can tell fluids are those when shear stress is removed, fluid original form cannot be attained, or partially. These properties of fluids, or this property of fluids, is known as zero memory behavior. So, zero memory behavior is a behavior of fluid not returning to its original form of original shape when the shear stress is removed. It would continue to flow forever and ever. Okay, so you can just pause and write definitions. Moving ahead. Now we'll be understanding concept of continuum. Here we will be getting introduced to what is Knudsen number and things like that. Okay, so we all know. So I'll be skipping a bit part and I'll be writing direct lambda equals to mean free path. So this is basically the average distance a molecule can travel before colliding to any other molecule, or it can be explained the minimum distance a molecule can travel between two successive collisions is known as mean free path. For further understanding, you can Google it. What is mean free path? And L is the characteristic dimension. So L actually is the characteristic dimension and it depends on the problem. So if you take, I will just explaining what is L here taken. Fluid flowing through a pipe of diameter D. So the L equals to characteristic dimension would be D as this length is taken. So from here we get lambda by L is known as Knudsen number. Okay, so this is known as Knudsen number. So first thing we understand why it is important to understand what is Knudsen number. Okay, so Knudsen number is a specific number which gives the fluid flowing or the fluid is actually valid for continuum or not. Here some conditions will be there, so understanding it, Knudsen number. So if your lambda by L is less than 0.01, it is considered that continuum is considered to be valid, and if your L is between 0.01, so if your Knudsen number is between 0.01 and 0.1, and if your lambda by L is from 0.1 to 10, and if your lambda by L is greater than 10. So for these cases we can write slip flow. So we'll be understanding these technical terms ahead in a more fine way. What do slip flow mean, continuum mean, and the physical significance of them. So yeah, it is a theory you can write. Just writing down. This here is known as transition flow. Transition between slip flow and free molecular flow. So yeah, this will be free molecular flow. So yeah, this is just the theory of the Knudsen number. The Knudsen number is important because it tells us whether the fluid you are considering are the continuum is applied or not, slip flow is applied or not. It lies in which range. Okay. So in this course, we'll be only studying the fluid in which continuum is valid. For the red, you will know why continuum is important and why it's only studied usually. Okay, so yeah, we'll be moving further. moving ahead, the most well-known topic, and I hope you had studied it also before, viscosity. Viscosity. So yeah, for understanding it, we can make a flow of water like this. This water, and we can understand as a water or a fluid as layers. As you can see, these are layers, individual layers. 1, 2, 3, 4, 5, 4, and y-axis, x-axis. This is height y, and the velocity u varies with y. Okay, so here we can say if a force is applied on a top, or that is shear stress in a better way, shear stress tau is applied on a top, applied on top of a fluid, then we can write it as shear stress is proportional to du by dy. Okay, so we'll be understanding how I wrote this and how the proportionality came. Fine, which you can say, let us consider a fluid which is not flowing at all. It's a fluid which is not flowing at all. Either I'll draw a better picture, or we can just understand from here. Just assume or just think the shear force is applied on the first layer, then why the second layer would move? It would actually move due to the force applied by first layer on second, and this force would actually, you can understand it as a friction force due to fluid or due to the particles. So this layer would move because there would be a front line force or shear stress applied on this particular layer by the above layer. So as you can think here already that a force is applied on second layer on this direction, so naturally a backward force, shear stress, is applied on the above layer. So yeah, so upon experiments we can tell shear stress is proportional to du by dy. This is also known as velocity gradient. Okay, so shear stress. So removing the proportionality constant, we can write it is equals to mu times du by dy, and yes, mu is known as coefficient of viscosity. So yeah, mu is defined as coefficient of viscosity, and understanding it by this formula, you can actually know the physical significance of the shear stress, the coefficient of viscosity, by replacing and transforming this formula a bit by writing mu equals to shear stress divided by du by dy, shear stress divided by velocity gradient. Velocity gradient. Okay, so yeah, from this formula we can understand, or from this formula, if we plot a graph of shear stress by velocity gradient, we get a straight line. So yeah, understanding from this formula, you can tell them, and you can already see that shear stress by velocity gradient, coefficient of viscosity, is actually the slope of shear stress by velocity gradient, that is theta. So now, understanding it a bit more, I will be understanding a definition that the fluids in which coefficient of viscosity is constant, means the slope isn't changing here, are termed as Newtonian fluid. So yeah, you now understand what are Newtonian fluid. Newtonian fluids are those fluids in which shear stress by velocity gradient does not change and is constant forever. So these types of fluids are known as Newtonian fluids. For example, water. And many examples can be taken. Okay, so now moving ahead. But there are also fluids which aren't Newtonian. There are also non-Newtonian fluids. So yeah, understanding non-Newtonian fluids. So general equation of shear stress. So yeah, general equation of shear stress is defined as shear stress is equals to m times du by dy to the power n. Yeah, this is the general form of shear stress. This is known as flow index behavior and n is known as flow consistency index. Okay, so n is termed as flow consistency index and m is told as flow index behavior. Okay, so from here, so this is a general relation for all the fluids, for Newtonian, non-Newtonian, both. Okay, this relation was found by a scientist known as Oswald de Velde. So the equation is named after it. Oswald de Velde relation or equation. Okay, so plotting the graph of this, you can tell shear stress upon du by dy. Okay, so I'll be asking a question whether is tau divided by du by dy equals to mu coefficient of viscosity always true. So I am asking it, is this relation always true even for general fluids, for the Oswald de Velde relation, the fluid which follows this? All the fluids follow this, but is this valid for everyone? Newtonian, non-Newtonian means this is always equals to coefficient of viscosity irrespective of whatever fluids you are taking. Okay, so before answering the question, I will draw a graph. So if you put n equals to 1 in this equation, putting n equals to 1, we get tau equals to m du by dy. This is Newtonian fluid. So we can tell m is equals to mu here. Newtonian fluid. Okay, so now we will be considering a case. So just think, if you put n is less than 1, we get a graph something like this: n less than 1, graph like this, n greater than 1. Okay, so if you would plot, you would get these kind of graphs. Okay, so if n is greater than 1, the particular fluid is known as diluent fluid, and if n is greater than 0, it is known as pseudoplastics. Pseudoplastics. Okay, so there is also one more kind of fluid which I would be explaining after telling the answer of this question. So yeah, what do you think? Is it always true even if the fluid is the diluent fluid, or pseudoplastic means non-Newtonian fluids? So the answer is yes. Just think coefficient of viscosity as the slope of shear stress versus the gradient of velocity du by dy. So yeah, as you can see, pseudoplastics and diluent fluids means in non-Newtonian fluids, coefficient of viscosity keeps on changing. Means if I want coefficient of viscosity of pseudoplastic at this point, I'll draw a tangent, the angle theta, the differential when we differentiate shear stress with respect to velocity gradient, we'll get viscosity. So at this point, viscosity would be equals to theta 1 on a point further. So if you would extend, you will get an angle theta 2. Okay, so this way the shear coefficient of viscosity keeps on changing for both dial length and pseudoplastics. Okay, so yes, it is always valid and all set. So as you can see, this equation is always valid. The shear stress by velocity gradient is equals to coefficient of viscosity. This equation is always valid. This is known as Oswald-Vieira relation, flow consistency index, flow index behavior, dialect fluid, pseudoplastics, general equation. So yeah, moving further ahead.